delta G sub F, 0 kilojoules per mole. And here it's not a delta, and there's no F. This is S0, that's the absolute value of entropy, and this table is at 298.15. Okay? That just happens to be not the standard temperature, as I keep emphasizing, but a convenient temperature. Everybody knows what the standard states of the phases of the elements are. So notice these are absolute values, these are relative values, and they depend on the definition that the enthalpy of formation of the elements is 0, and also the free energy of formation of the elements is 0. Okay. So that's what you see in the tables in the back of the book. And when I'm giving you problems on the quiz, I give you selected numbers, and I give you tables, and I leave things blank. And whatever I leave blank, that's the thing you have to calculate. Okay? So now I want to talk about free energy, and it's referred to as Gibbs free energy. And we use the letter G. It's a combination of the enthalpy and the entropy. And this is what we're going to use to determine whether or not reactions are spontaneous. As I said earlier, if we look at the entropy of the universe, in any spontaneous reaction, the entropy of the in any reaction, not any spontaneous reaction, in any reaction, the entropy of the universe is going to increase. That's what the second law states. And when you talk about the universe, of course, it makes life tough because you can't really measure things in the universe. And we want to talk about the system, okay? So we want to, this is a property of the system, this is a property of the system, this is a property of the system. Now the big thing is, we can't measure absolute values of this, we can't measure absolute values of this, we certainly can measure absolute values of this. But we can measure changes in this. And so the equation we're going to use to calculate things, delta G is this. And we're just going to look at the combination of enthalpy and entropy changes. We already talked about some spontaneous processes. For most of the ones we know about, if you have a negative delta H, the system's going to lower energy, you'd say that's spontaneous, but we found some exceptions. The entropy change for the system can be positive or negative. If you're going from the gaseous state to a liquid state, it's going to be a negative entropy change. Okay. So we have to look at the combination of these two to look at calculate delta G, and we'll say something about how we can relate delta G to spontaneous processes. So the first thing, as I said, I can do this calculation for entropies. Instead of saying delta H sub F here, I just say S0. I wouldn't put a delta in there. I can do this for free energy changes. Notice one of the things is, because of this definition, we can't measure enthalpy changes for elements, so we define them to be 0. The same thing is true about this. And that's by definition. We can't argue this. But what about S0 for elements? What type of number is it going to be? going to be a positive number always. It's equal to 0 at absolute 0. That was the third law of thermodynamics. Anytime you talk about an element at a higher temperature, 298, 0, whatever temperature you want to pick, it has to be a positive number. This is the thing. I want to talk about delta S0 for a reaction. It can be positive, it can be negative, it might even be 0. Highly unlikely, but I'm trying to think of that type of reaction where it might be 0. It's not likely to be 0 for a reaction. Okay. But it can be a positive or a negative number, depends on how disordered the products are, how much randomness there is in the products compared to the reactants. And we have a table, like I just showed you. You can always calculate S0 for a delta S0 for a reaction. It's the sum of the products, the S0 for the products and reactants. But the important thing is, if I leave a blank space in the table for the entropy of an element at 298, which is mostly the temperature we'll work at, that means you have to calculate it because it's not 0. I gave you the table at 0 kelvins, then you could write down 0. Okay? That's all I'm trying to point out here. So, the next set of steps here, and I'll do this here. Sometimes I do it myself, and sometimes I do it this. And we're confining ourselves to chemical reactions, but in any chemical reaction, we can say the entropy change for the universe is equal to the entropy change for the system plus the entropy change for the surroundings. Okay? And if it's a spontaneous process, if something's happening, this will be a positive number. In fact, this can only be a positive number. Because either nothing's happening, in which case delta S is 0, or something's happening, delta S for the universe is positive. Second law of thermodynamics. So he says, there's the second law of thermodynamics. For anything that happens, delta S of the universe is positive. Oh, there's one thing I wanted to do that I didn't do, and this just reminded me. So I'm going to set this off for a minute and go way back in history. Somewhere we looked at what we call the adiabatic process already, and I'm going to go all the way back to delta U. U plus W. And if I know the heat change, and I know the work, and I gave you two equations for that, I can calculate the entropy, the internal energy change for the universe. Now, one of the types of processes we talk about is an adiabatic change. Adiabatic means there's no heat exchange between the system and the surroundings. That's the prefix somewhere. What does that tell you? It tells you Q is 0. Q for the system is 0, Q for the surroundings is 0. Adiabatic, that's the heat change between the system and surroundings. And that means in that particular type of process, the change in internal energy must be equal to the work done by or on the system. Then the other thing we like to talk about when we're combining things in thermodynamics isothermal changes. Means I could put a capital T, it doesn't matter since I put a delta there, it's the same number. But the temperature change is 0. Now, this has an implication in the following fashion. U is proportional. The internal energy change is proportional to the absolute temperature. Okay? You have a higher absolute temperature change. I guess I should put delta U and delta T because you can't measure the absolute values. But if I measure, if there's a change in temperature, there has to be a change in U. And they're proportional. Now notice, if it's isothermal, what does that say about U? And we always say for ideal gas. So if you have an adiabatic and isothermal process and you're dealing with an ideal gas, what can you say is happening? Nothing. That's why I went back, that's what reminded me when I saw the entropy change for the universe. So people always talk about adiabatic changes for isothermal gases, for ideal gases. That means Q is 0, that means the internal energy is calculated from the work change. On the other hand, if we say isothermal, it means delta U is 0, and these two numbers are equal but opposite in sign. So the work done on the system is exactly equal but opposite in sign to the heat added to the system. Okay. That's how you get delta U is equal to 0. But if you have both of these things happening, it says Q is 0, delta U is 0, that means W must be 0, and the system isn't doing anything. Or the system. I just like to point that out. It's an exercise, whatever they do with thermodynamics, where they play games with these different words. Okay, so I just wanted to do that. Let's go back to what we're doing now. I was supposed to mention that a couple of weeks ago, and I forgot that. But here we go. We're talking about the second law of thermodynamics. Anytime you have a change, the delta S plus, delta S for the universe increases. That means delta S system, delta S surroundings are both positive numbers. Or the sum of those two is a positive number. And here we say we're only doing pressure volume work. Notice we make these restrictions and we come up with some result. Then if we're doing partial differentials, we can go back and see how the modifications can affect our results. That's what thermodynamics is all about. But it's way beyond what we're going to do. We're just deriving some basic law we can use. So if we're working at, if we're only doing pressure volume, in other words, chemical reacting systems expanding and contracting, the Q of the surroundings is minus the delta H for the system. Should have the other case, the other thing up there. But as in other words, the minus sign says, as the system is losing heat, the surroundings must be gaining heat. Okay. Losing heat, put a positive number for the system, but the minus in that definition says the surroundings has the opposite sign. Okay? Question? And that's Q sub P, because that's what we said for the definition of delta H a long time ago. And we can make it a reversible change. That's the way we did that. Well, that's the definition we used. We said delta H for the system is equal to minus Q sub P that we measure at constant pressure. We make big surroundings. There's going to be a very small change in temperature. He's doing that so he can do integration if he wants to, but he's not going to in this text. So you have Q of the surroundings minus Q sub P, divide that by the temperature. That's the heat change reversibly done over absolute temperature. Or we can say it's delta H for the system, and that minus goes in because we're talking about the surroundings. So now notice what he did. That first equation said delta S for the universe is equal to delta S system plus delta S surroundings. And this is what we said for the surroundings in terms of something that happens to the system, just by changing the sign and making things reversible and all of that. Okay. Then he's going to multiply to get rid of the t. In other words, we're going to end up with the equation that looks like I wrote just a minute ago. And that's all it is. This is justifying that equation. As I say, some books say, let's just define. That's what Gibbs says. So let's define a new property. It's delta H minus T delta S. So he multiplied across by T, and he has T delta S for the universe, T delta S for the system. Remember, in the previous slide, the absolute temperature was in the denominator here, so all I did was get rid of the absolute temperature. Okay. And then he changed signs, so it looks like the equation I wrote just a minute ago, and he made this minus, this became a positive, this became a negative. And now we talk about T times delta S for the universe. We still can't measure it, but we're going to call it delta G. Okay, so this side is going to be what we call delta G. This is about the universe, this is about the system, and now we can make some statements here. We know that minus T delta S has to be a positive number. Actually, delta S has to be a positive number, minus T delta S has to be a negative. And we write it like that. I think I did just a minute ago. And so all we're doing is saying this number represents something that happens to the universe. And he's going to put in the delta signs. There we go. Which is the definition that Gibbs basically wrote for his free energy function. And the rationale now is we can look at this number here. And for a spontaneous process, this is positive. That makes delta G with this minus a negative number for spontaneous processes. It says that. Delta S is still positive, but the minus T delta S makes delta G for the system a negative number. And it's sort of a jump going from the universe to the system, but that's what he did, and it worked. That's all we need to know. And here's the important thing. Anytime you want to decide if something is spontaneous, you calculate delta G. If delta G comes out to be a negative number, then the reaction you're talking about is spontaneous. If delta G comes out to be a positive number, the reaction is not spontaneous. And what happens if you get delta G equals 0? That's the condition for equilibrium. How about that? So now we could use delta G to calculate the equilibrium constant. Oh, if delta G is 0 for the system, when the system is at equilibrium. Let's see. I don't think he did this in the next slide. I don't know. Well, you can look at this slide. Basically, it says here are the different cases. If delta H is negative, right, that means the energy is being lowered during the process. That wants to occur spontaneously. If delta S is positive, more disorder. That occurs spontaneously. That means if both of these, if this is negative, this is positive, the reaction is going to be spontaneous at all temperatures. Because delta G is equal to delta H minus T delta S. Notice if delta H is positive in a reaction, it means that doesn't want to happen because it's going to a higher energy state. Delta S is negative in a reaction, it means that doesn't want the reaction to occur spontaneously because it's going to more ordered state. It's going to a higher energy state, lower order. Both of those are non-spontaneous. Together, they give you reactions that are not spontaneous at any temperature. Notice he says 3O2 going to ozone is always going to be a non-spontaneous reaction. You say, how do you get ozone? You run lightning through oxygen and it reverses that process. But now you've introduced something from the outside. That's not the spontaneous reaction. You made it happen by sparking lightning or electrical discharge through oxygen. Spontaneously, what's eventually going to happen to the ozone? It's going to revert back to oxygen. So you can make a non-spontaneous reaction because you're introducing something from the outside. And then here are the two things that change from spontaneous to non-spontaneous as you change the temperature. In one case, where delta H is negative and delta S is negative, these two negatives make a positive. So as you raise the temperature, this term becomes more important than this term. and the reaction goes from a positive to a negative delta G, and so it's non-spontaneous at high temperature, spontaneous at low temperature. And the reverse of that, if they're both spontaneous, as you raise the temperature, since there's a minus in front of T delta S, this number is going to get bigger and bigger until it's bigger than this one, and now you have a lot smaller, more negative number, let's put it like that. So it's going to be spontaneous at high temperature, non-spontaneous at low temperature. So this is how you can decide if a reaction is going to work by raising the temperature, or by lowering the temperature, or temperature has no effect. You have to look at both terms, or memorize the table, which is sort of confusing. Okay, this is the definition of standard free energy of formation then. There it is. Products minus reactants, the same old thing. Elements are going to be 0, and I've still got 2 minutes. Oh, it says the end of the show.